Every year, millions of tons of mineral wool are produced worldwide, a material known as a stone sweater for houses. In the United States alone, this industry is valued at over $4 billion and is rapidly growing. But have you ever wondered how cold, heavy volcanic rock transforms into a light fluff that protects our homes from cold, fire, and noise? We will embark on a journey from dark basalt quarries to scorching furnaces where stone melts in miniature volcanoes, and to the moment it becomes a fluffy cloud of fibers. But the most interesting part awaits at the end, a fact that will turn your understanding of this material upside down. The mineral wool market in the United States is a huge machine that turns over billions of dollars. We're talking about an industry worth more than $4 billion a year, and it continues to grow. This means that across the country, from the cold northern states to the hot southern ones, more and more builders and homeowners are choosing this exact stone sweater for their walls. It all starts in a quarry. Although it's not that simple, because at the end of the video, you'll learn another interesting fact. In the quarry, we're interested in basalt, a dark, heavy volcanic rock. This is the same material that makes up the ocean floor. Along with basalt, another unexpected ingredient comes into play: slag. This is a byproduct of metallurgical plants, a solidified melt that used to be simply thrown away. And now it's a valuable raw material. So, our recipe? We take a few parts of basalt, add a bit of slag for the right chemistry, and sometimes we throw in a little old glass or recycled mineral wool for environmental friendliness. All these stone ingredients are brought to the factory and loaded into a giant bunker. And now the real inferno begins, in a good way. From the bunker, this mixture is fed into a furnace called a cupola furnace. Inside a huge vertical tower, a fire burns continuously. This is a miniature volcano, created by man. Our stone mixture and coca special fuel that burns with incredible heat are loaded in layers. Powerful fans blow air into the furnace, raising the temperature to absolutely cosmic levels, 2,700 degrees Fahrenheit. This is hotter than the lava that erupts from a volcano. At such a temperature, the stone has no chance. It melts, turning into a liquid, white-hot mass. This fiery river flows down into a special trough and out of the furnace, like water. The sight is simply mesmerizing. A bright, dazzling stream of molten stone from which such heat emanates that it's hard to stand nearby. This is where the transformation of heavy liquid into light fluff happens. This process is called fiberization, and it's brilliantly simple. You've seen a cotton candy machine, right? It has a rapidly spinning center where sugar is poured. Well, here it's almost the same, only instead of sugar, it's molten stone. A thin stream of this stone lava falls onto several discs that spin at a frantic speed, making thousands of revolutions per minute. When a drop of molten stone hits such a disc, centrifugal force instantly stretches it and throws it to the side in the form of an incredibly thin fiber, a few microns thick, thinner than a human hair. Since this process is continuous, a whole cloud of glowing stone threads flies off these discs. It looks like a glowing, golden chaos. Billions of these finest fibers, cooling on the fly, turn into a light, wool-like mass. Our heavy molten stone has just become airy and fluffy, but for now, it's just a formless cloud of fibers. If left as is, it would simply fly apart. To hold it all together, glue comes into play. While the fibers are still flying in the air in a special chamber, a fine mist of a binder is sprayed onto them. This is a special resin, similar to glue, which coats every tiny fiber. It's like applying hairspray for hold, but on an industrial scale. This cloud of glue-soaked fibers flies on and enters a deposition chamber. At the bottom of this chamber is a wide, moving conveyor with a perforated belt. Powerful fans draw air from under the belt, creating a vacuum. This airflow pulls the fibers down and lays them evenly on the conveyor, forming a thick, fluffy mat. This already looks like the future insulation, but it's still soft and the glue on it hasn't hardened. The thickness of this mat is regulated by the speed of the conveyor. The slower it moves, the thicker the layer that manages to settle. But let's talk about its superpowers. The first and most important is fire resistance. This is a true fireproof shield. Mineral wool, made from basalt, begins to melt only at temperatures exceeding 2000 degrees Fahrenheit. Now this golden yellow, fluffy mat, resembling a giant biscuit roll, is ready for the final stage baking. It slowly enters a huge furnace called a polymerization chamber. This is a long tunnel, inside which a temperature of about 400 degrees Fahrenheit is maintained. The goal of this stage is not just to dry the mat, but to bake the glue. The resin polymerizes under the influence of temperature. That is, it turns into a hard, durable plastic that firmly glues the stone fibers together at their intersections. It is in this furnace that mineral wool acquires its final properties. It becomes resilient, returns to its shape after compression, and gets its structure. During this process, the resin often changes color, giving the final product its characteristic yellow-brown hue. From the other end of this giant toaster furnace comes not a fluffy mat, but a solid, resilient mat of a given thickness and density. But it's still an endless ribbon. It's time to give it a commercial appearance. This hot mat passes through a whole system of cutting tools. Sharp disc saws or powerful knives with incredible precision cut it lengthwise and crosswise into sheets or rolls of standard sizes. For example, 16 or 24 inches wide, so that they fit perfectly between the studs of a frame house. The edges are trimmed, and now we have a familiar product. And here another little magic happens. Packaging. The finished mats or rolls are fed to a packaging line. A special press compresses them, removing almost all the air. The volume of the product can be reduced several times. Then, this compressed block is quickly wrapped in durable polyethylene film and sealed. This is done to save space during transportation. It's like a vacuum bag for clothes. Instead of a huge fluffy roll, we get a dense, compact package. And when a builder at a construction site cuts the film, the mineral wool will hiss, take in air, and, like a spring, expand to its original size. The finished packages are stacked on pallets by robotic manipulators, wrapped in stretch film, and forklifts take them to the warehouse or directly into the back of a truck. And so, when another truck, loaded with these light but so effective packages, leaves the factory gates, our journey is complete. We have traced how ordinary hard stone, having passed through the fiery heart of the furnace and turned into cotton candy, has become a high-tech cocoon that will keep warmth, quiet, and safety in someone's home for decades to come. And now for the most interesting part about environmental friendliness, because here mineral wool simply breaks all the molds. We've already said that it's made from stone and slag. Well, on average, modern mineral wool consists of 70% recycled raw materials. Sometimes this figure reaches 90%. Imagine, 3/4 of your insulation is essentially industrial waste that has been given a second life. This is millions of tons of metallurgical slag, which used to be simply taken to landfills, and now it's turned into a high-tech product. This is one of the brightest examples of a closed-loop economy, where the waste of one production becomes a treasure for another. Giant factories, such as Rockwool or Owens Corning, annually process so much slag that it would be enough to fill thousands of Olympic swimming pools. This is a true feat of industrial recycling. The second superpower is acoustics. Due to its dense, chaotic fibrous structure, mineral wool is an incredible sound insulator. It doesn't just block sound, it absorbs it. When sound waves enter the thickness of the material, they are forced to pass through a labyrinth of billions of stone fibers, losing their energy and fading away. That's why they love to use it not only in residential buildings to protect against noisy neighbors, but also in professional recording studios, cinemas, and even between floors to not hear stomping from above. It's like building a personal, silent mode into the walls. Every year, over 130 million tons of glass are produced worldwide, a weight equivalent to 1.3 million Eiffel Towers. Imagine, mountains of broken glass, taller than skyscrapers, are transformed into crystal clarity thanks to fires of 3,000 degrees and laser snipers that knock out impurities at a rate of thousands of shots per minute. From ancient glassblowers who breathe life into red-hot bubbles, to futuristic tin baths where glass is born perfectly flat like a mirror. But behind this symphony of fire lies a secret. What if glass holds the secret to eternal reincarnation, which will allow us to turn the world upside down? Watch until the end, and you'll find out something you never imagined about this transparent, amazing material. Ready for the journey? Although the vast majority of architectural glass today is born from a perfectly flat, fiery river flowing over molten tin in the float process, the true soul of the material is revealed in methods that give it character and uniqueness. This path from a simple transparent sheet to a work of decorative art is a fascinating journey. To create glass with individuality that carries the imprint of a human touch, masters still turn to techniques that have existed for centuries. A glassblower dips his long, hollow pipe into a furnace where a mass of sand and other minerals boils at a temperature of 2,000 degrees Fahrenheit. He gathers a honey-like ball of molten glass on the end of the pipe, and, skillfully rotating it, begins to blow air into it. The initial bubble, born from his breath, gradually transforms into an elongated, glowing hollow cylinder. Thanks to the force of gravity and skillful swinging, this cylinder can reach a length of several feet. After the ends of the cylinder are cut off, it is cut lengthwise and placed back in the furnace. There, under the influence of heat, it slowly unrolls, like a scroll, and the masters smooth it into a flat sheet. Glass born in this way is never perfectly flat. It lives its own life, retaining barely noticeable waves, tiny air bubbles, and thin lines that tell the story of its fiery birth. This glass has a watery, organic quality that cannot be replicated by a machine. But the creation of unique glass does not stop at forming the sheet itself. Other methods transform ordinary sheets into complex decorative elements. Fusing or sintering allows artists to literally paint with glass. Multicolored pieces of glass are laid out on a base sheet and sent to a furnace, where at a temperature of 1,500 degrees Fahrenheit, they merge into a single whole, creating bright, painting-like compositions. Closely related to this is the process of slumping or bending, where a flat sheet of glass is heated until it becomes soft and sags under its own weight, taking the shape of a ceramic or metal mold lying beneath it. This allows for the creation of curved panels and three-dimensional glass sculptures. Modern technologies add even more possibilities. Lamination allows for baking colored films, fabrics, or even thin sheets of metal between two sheets of glass, creating endless variations of color and texture. Sandblasting and chemical etching remove the top layer of glass, making it matte and creating complex patterns on its surface, from simple geometric shapes to photorealistic images. Thus, by combining ancient crafts with advanced technologies, modern production transforms simple glass into an expressive architectural material, capable of shaping light, color, and space. In the modern world, where tons of used glass containers are collected daily, the path from the trash can to a new bottle is not just remelting, but a high-tech odyssey, controlled by computers and light. Imagine a mountain of broken glass, reaching a height of tens of feet, where transparent, green, and brown fragments are mixed with labels, caps, and ceramic impurities. Turning this chaos into pure, raw material is a task for a whole complex of smart machines. It all starts with mechanical crushing, where steel hammers turn bottles and jars into fragments a few inches in size. This stream of glass, resembling a moving river, embarks on a journey through a labyrinth of sorting systems. First, powerful magnetic separators pull any steel impurities from the stream, and then eddy current systems literally shoot out aluminum caps and foil into separate containers. Powerful air currents blow away light paper labels and plastic remnants. But the most difficult task lies ahead: removing impurities that are almost indistinguishable from glass in weight and size, such as pieces of ceramics, stone, or porcelain. These enemies of glass do not melt at standard temperatures and turn into defects in new products, so their removal is critically important. This is where optical sorting comes into play. The glass fragments are accelerated on a conveyor belt to a high speed and fly through a scanning zone. For a fraction of a second, each fragment is illuminated by bright light, and high-speed cameras take hundreds of pictures. A computer system with lightning speed analyzes the images, identifying foreign bodies by their transparency, structure, and shape. As soon as the system spots an opaque piece of ceramic, it instantly calculates its trajectory and gives a command to a battery of air nozzles. A precise, sniper-like stream of compressed air knocks the unwanted element out of the general stream, sending it to waste. This process is repeated thousands of times per minute. In parallel, an equally important sorting by color takes place. The same optical systems analyze the spectrum of light passing through each fragment. The machine distinguishes between crystal clear, rich green, and deep brown glass. Depending on the set program, the system can, for example, select only transparent glass, knocking out all colored fragments with air jets, or separate the stream into 3 separate color fractions. As a result, at the output, a perfectly clean, color-sorted raw material is formed. Cull it, ready for a new life without loss of quality, which is the pinnacle of the modern circular economy. Then, flat glass can be made from this raw material. The birth of modern flat glass is a symphony of fire and precision, a spectacular process that transforms ordinary raw materials into perfectly transparent sheets. It all begins in a huge melting furnace, the fiery heart of the factory that operates continuously for years. Into this furnace, resembling a lake of molten fire, a carefully dosed mixture, or batch, is loaded, consisting of pure quartz sand, soda ash to lower the melting temperature, and limestone for stabilization. To this is added a significant amount of cullet, or crushed recycled glass, which helps to speed up the melting process. Inside the furnace, at infernal temperatures approaching 3,000 degrees Fahrenheit, these solid components slowly transform into a homogeneous, viscous liquid. The melting process is strictly controlled to ensure the complete dissolution of all particles and the removal of gas bubbles, creating a flawlessly clean melt. From the furnace, this stream of red-hot to bright orange-colored glass, resembling a river of lava, smoothly flows into a bath of molten tin. This is the culmination of the process, known as the float process. The tin bath, stretching for hundreds of feet in length, has a perfectly smooth, mirror-like surface. Since glass is lighter than tin and does not mix with it, it spreads over the surface, forming a perfectly flat ribbon of uniform thickness. Gravity levels it from below, and surface tension smooths it from above, creating impeccable optical quality. The speed at which this ribbon is pulled from the bath determines its final thickness with an accuracy of a fraction of an inch. After forming a perfectly flat surface, the glass ribbon, still very hot but already solid enough to hold its shape, enters the most tranquil but critically important stage: annealing. It enters a long tunnel known as an annealing layer. If the glass were cooled too quickly, its surface would contract faster than its interior, leading to the creation of huge internal stresses that would make it brittle and prone to cracking. In the layer, however, the temperature of the glass is slowly and controllably reduced over several hundred feet, from over 1000 degrees Fahrenheit to room temperature. This process allows the entire sheet, both surface and core, to cool evenly, relieving all internal stresses. From the other end of the layer emerges a single, flawless, continuous ribbon of completely transparent, stress-free glass, ready for automatic cutting into huge sheets that will become the windows, facades, and doors of our world. Every year, over 3 million hand grenades are produced worldwide, and each one goes through dozens of stages, from melting metal to precisely dosing explosives with an error of less than 1,000th of a gram. There's no room for error here. Temperature, pressure, humidity, everything is under control. But what exactly happens behind the walls of classified workshops? How is simple metal turned into a deadly tool with a mathematically precise geometry of destruction? If you watch this video until the end, you'll learn about technologies that keep even national aeronautics and space administration engineers on edge. Despite strict restrictions and high danger, every step of production takes place in specialized conditions, with the use of advanced technologies that ensure the safety of workers and the high quality of the final product. First, in the production of explosive grenades, components are used, each of which has a clearly defined function and industrial standards. Although the exact recipes of the explosive substances themselves, such as trinitrotoluene, penthrite, or RDX, are secret due to their extremely dangerous nature, it is known that these substances are made from a mixture of chemical reagents that go through several phases of purification and stabilization. The production of these components takes place in controlled reactors with strict adherence to temperature and pressure regimes, where even a small error can lead to an accident. Metal blanks undergo primary processing. They are cleaned, brought to the required temperature, and if necessary, alloying additives are added to achieve the specified characteristics of impact toughness and hardness. The next key step is the forming of the grenade shell itself, which is done either by high-pressure die casting or cold stamping. In die casting, the metal is brought to a liquid state and poured into a complex steel mold, several to 5 feet long, under enormous pressure, up to 20,000 psi. These molds already account for the necessary relief details and seating for the fuse and explosive charge. An alternative method is cold forming, where pieces of sheet or bar metal weighing 1 or 2 pounds are pressed in dies with powerful mechanical presses. The pressure can reach 30,000 psi. This creates a capsule of precise geometry, with walls averaging 1/10 of an inch thick, but with options for reinforcement in critical zones. One of the most important elements is the final surface treatment of the body. The grenade body undergoes milling, grinding, and also mandatory creation of a relief texture. This is either scoring or a solid textured grid, which together with internal concentric grooves, ensures predictable fragmentation into hundreds of sharp fragments with a diameter from 1/16 to 1/8 of an inch. It is this microstructure of the shell that sharply increases the effectiveness of destruction within a radius of 40 or 50 feet. After mechanical processing, each body is chemically and technologically strengthened. Heat treatment is carried out to increase impact resistance, and it is also galvanized or painted for corrosion protection. In large workshops, each part comes off an automated line, and operators monitor the process's accuracy through integrated sensors for measuring thickness, geometry, and distances between the scoring ribs. All this complex logistics, control regime, and special materials are aimed at only one thing, so that when the grenade is used, the body fragments uniformly, creating the maximum number of deadly fragments of a given size and shape. This is a modern approach to designing explosive devices, where even the surface structure has a critical significance for completing a combat mission and surviving in extreme conditions. The explosive substance, which determines the force of the explosion, is dosed in powder or granular form with an accuracy of fractions of a gram. This material is placed in the inner chamber of the body, where a special charge is made. The filling process is carried out in automated workshops under the close supervision of surveillance cameras with remote control. Around the explosive charge, the main initiation mechanism is placed, which consists of a detonator and a fuse. These mechanisms are high-tech devices that are activated when a lever is pressed or after a delay during the grenade's flight. The current level of automation in grenade production not only allows for increasing the speed of unit output, but also significantly reduces the risks of accidents. Security services constantly monitor temperatures, vibrations, and humidity levels in the premises. Both classic metal parts and the latest composite materials are used to create the internal mechanisms, which reduce the product's weight without sacrificing strength. One of the most complex stages is the integration of all components into a single structure. This resembles the high precision of a medical operation. Complex parts are assembled on assembly lines with an accuracy of thousandths of an inch. All operations take place in special rooms without access for unauthorized persons, using specialized tools. After assembly, each explosive device undergoes multi-stage testing. The tests include checking the body seal, functional testing of the detonation mechanisms, and evaluating the uniformity and reaction speed of the initiator. The production cycle of one unit of an explosive device can last from several hours to several days, depending on the model's complexity, the degree of workshop automation, and safety requirements. These products undergo several stages of strict inspection and quality control, which includes the use of X-ray scanners to check the internal structure, as well as conducting simulated impact tests under the control of artificial intelligence. Engineers involved in the development and production of this product are in constant close cooperation with military structures, receiving clear technical specifications and updated requirements dictated by changes in tactics and combat technologies. The body materials, explosive mixtures, and fuse designs are periodically updated to ensure maximum effectiveness and storage safety. The production of explosive devices is a combination of chemistry, metallurgy, mechanics, and electronics with the highest level of control over all processes. The continuous development of technology leads to the use of increasingly sophisticated computer simulation systems that allow for predicting the behavior of combat grenades in various use scenarios. The power of such devices is measured in pounds of TNT equivalent, where universal hand grenades can correspond to an explosion of about 0.5 pounds of TNT. The dimensions usually do not exceed 5 inches in length and about 3 inches in diameter, which makes the grenade compact and easy to carry in combat conditions. As a result of the production of these swift and versatile combat tools, every step is a balance of speed, accuracy, and safety, where the quality of the product and the lives of soldiers in battle depend on the operator's professionalism. This process is not just mechanics and chemistry, it is a complex discipline that requires deep knowledge and attention to every detail. The production of hand grenades is an important component of the defense industry, with continuous improvement of technologies and control, which repeatedly sets new standards of quality and safety. It is thanks to this technical level that being true to one's task ensuring maximum effectiveness on the battlefield becomes possible. But what is the most important thing in the production and use of hand grenades? That's right, avoiding accidental detonation. It is known that the modern evolution of grenades is associated with the introduction of insensitive munitions that are more resistant to mechanical impacts and temperature fluctuations, which reduces accidents and losses from unauthorized explosions. Over the past 20 years, the share of such impact-resistant products in new Western contracts has exceeded 50%, and the number of incidents with accidental detonation has been reduced by more than 70%. An impressive figure, isn't it? The number of grenades used in military operations and training varies depending on the intensity of combat actions. For example, during active phases of major armed conflicts, the consumption of hand grenades can reach thousands of units per day for one large formation, while for training and range firing, from 1 to 3 million grenades are used globally per year. A significant portion of the finished products is exported, and in some years, the share of exports can exceed 60% of the total output. Every year, over 30 million tons of bamboo are harvested worldwide. But did you know that this seemingly ordinary grass can transform into steel, silk, and even concrete? It grows faster than any tree, absorbs more carbon dioxide than a forest, and doesn't require replanting. But the most interesting part is what's hidden inside its fibers. In this video, we'll show you how giant green stalks travel from plantations to ultra-durable flooring and delicate fabric. And if you watch until the end, you'll learn one shocking fact that will change your perception of the future of ecology. It all begins on vast bamboo plantations, covering millions of acres around the world. These are not chaotic thickets, but carefully managed farms. Unlike forests, bamboo does not require replanting. When one stalk, or culm, is cut, its extensive root system, called a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. One plantation can yield harvests for decades without harming the soil. Moreover, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only mature stalks, whose age can be easily determined by color and texture. Young shoots are left to grow further, ensuring the continuity of the cycle. One such mature stalk can reach 60 feet in height and weigh over 100 pounds, making its transportation from the plantation to the primary processing plant a complex logistical task. When these green towers arrive for processing, their radical transformation begins. First, the long stalks are cut into manageable sections. Then, they are fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to remove the outer greenskin and inner nodes, leaving clean, light bamboo planks. But inside these planks still lurks an enemy of durability: starch and sugar, which are a favorite food for insects and mold. To get rid of them, the planks are submerged in huge vats of boiling water, or a hydrogen peroxide solution for several hours. This hot bath not only sterilizes the bamboo, but also washes out all the nutrients. After this, the planks are sent for drying. Some producers dry them in the open air, but for industrial scales, they are loaded into giant kiln dryers, where they spend several days until their moisture level drops from 50% to an ideal 8 or 10%. This stage is critically important, as any residual moisture can lead to warping and cracking of the finished product. But the journey from a 60-foot pole to a smooth floorboard requires even more impressive engineering. The dried planks pass through milling machines that give them a perfectly rectangular shape. Then begins a process similar to making industrial lasagna. To create horizontal flooring, the planks are laid in a single layer and glued under pressure. For vertical flooring, the planks are placed on their edge and pressed from the side, creating a denser pattern. But the real marvel is the strand woven technology. Here, the bamboo planks are not just glued together, but completely shredded into long fibers, mixed with an environmentally friendly resin, and loaded into huge steel presses. Under infernal pressure, reaching 3,000 pounds per square inch, and high temperature, this mass transforms into an extremely dense, monolithic block. The hardness of such flooring on the Yanka scale can exceed 5,000 units, making it more than 3 times harder than oak, and more resistant to scratches and dents than most traditional wood species. However, hardness is only one of bamboo's facets. Its other superpower is the ability to transform into something incredibly soft and silky. The process of creating bamboo fabric is a true industrial alchemy. The most common method, known as the viscose process, begins with grinding the bamboo raw material into a cellulose pulp. This pulp is then submerged in a sodium hydroxide solution and then carbon disulfide, which turns it into a thick, viscous liquid. This liquid, resembling honey, is forced under pressure through the finest holes of a metal plate called a spinneret. Imagine a microscopic shower. Emerging from the holes, the thin streams enter a bath of sulfuric acid, where they instantly solidify, turning into endlessly long fibers. These fibers are then washed, bleached, dried, and twisted into yarn, from which fabric is woven. Despite the complex chemical process, the final product is biodegradable and has unique properties. It is extremely soft, hypoallergenic, has natural antibacterial properties, and breathes wonderfully, making it ideal for clothing and bedding. The global bamboo market is colossal and is projected to exceed $100 billion in the coming years. Annually, over 30 million tons of bamboo are harvested worldwide, and this figure is only growing. From kitchen cutting boards and toothbrushes to construction scaffolding capable of supporting the weight of concrete and elements in premium class cars, this giant grass demonstrates its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions for countless tasks, turning a fast-growing straw into the gold of the modern world. Bamboo grows both in the wild and on specially created plantations. Its natural habitat mainly covers tropical and subtropical regions of Asia, where it is an integral part of local ecosystems. At the same time, thanks to its unique properties and wide range of applications, bamboo is actively cultivated on plantations around the world. It is cultivated for the production of building materials, textiles, paper, interior items, and as a source of biomass. In the wild, there are over 1,000 species of bamboo. It is a perennial evergreen plant belonging to the grass family. Bamboo is known for its extremely fast growth. Some species can grow several tens of centimeters per day. Bamboo blooms very rarely, and after flowering and fruiting, the plant usually dies. Growing bamboo requires certain knowledge and care, including proper planting, regular watering, and choosing the right variety for specific climatic conditions. There are even ornamental types of bamboo that are grown in gardens and at home. Every year, over 100 million cubic meters of plywood are produced worldwide. That's enough to cover every roof in the United States with a whole tree. But few people know how this journey actually begins. Imagine, a wet log, still smelling of the forest, enters steaming chambers, passes through steam, knives, fire, and a pressure of 250 psi to become a wall, a roof, or even a stage. How is a log transformed into plywood that will last for decades? And what secret does the peeling process hide? If you watch until the end, you'll discover what they don't write in textbooks. The factory wakes up before dawn. With a deep roar, the gates open and trucks with freshly cut logs slowly drive onto the site. You should see them! Oaks, pines, poplars. True forest giants, long, thick, heavy, with wet bark and the aroma of a freshly felled forest. The wood is still breathing, still warm from the sun that shone on it for the last time. And so it begins. The logs are dumped onto a hydraulic feeder, where they move like logs in a mountain stream. Only instead of water, a system of rollers and chains is at work, and instead of a river, washing chambers, loud and ruthless. Bam! A jet of water under a pressure of 1000 psi, almost like a fire hose, hits the wood from all sides. All the mud, dust, and pieces of bark are torn off, like old skin. The logs spin, collide, foam, and hum. It looks as if the wood is undergoing a purification ritual before becoming something greater. After such a washing, they shine. But that's not enough. The wood is strong, rigid. You can't peel it like butter. So next, the steam chamber, a real wooden spa resort, but on an industrial scale. The logs drive onto an overhead crane, are lifted, and slowly submerged into giant cylinders, steam vats 60 feet long. And there, behind closed steel doors, begins what engineers call fiber softening, but I would call it wood stewing. Inside, it's 220 degrees Fahrenheit. The steam is thick, saturated. For 8 or even 12 hours, the logs soak in this environment. The steam penetrates to the core, the fibers relax, the resin starts to flow a little. And if you listen closely, it's as if you can hear the wood sigh, as if admitting, "Okay, I'm ready. Make me into plywood. Make me." They are taken out, and the logs are no longer the same. If at first they crackled with tension, now they are flexible, elastic like wet towels. Steam still billows from the bark, wood chips remain on the floor. The smell is like a sauna in the forest after a rain. They are stacked on roller conveyors and prepared for the next step, peeling, where they will lose their wooden identity, but acquire a new one. The log, fresh from the steam bath, is still smoking, as if someone just threw it from a pot onto the cold concrete. It is grabbed by a mechanical clamp, huge, like a transformer's paw, and lifted to the peeling machine. A giant with a steel mouth that is already humming, like a Harley-Davidson's engine at full throttle. This machine is a centrifugal peeling line, or simply put, a shredder. The log, heated and pliable, is mounted at the center of rotation, like a kebab on a skewer. It begins to spin slowly, then faster, even faster. And here the peeling knife comes into play, long, straight like a samurai sword, only made of steel and as wide as the entire log, 4 or 5 feet. And it doesn't cut. It peels, layer by layer, strip by strip. Screech! Shh! Vroom! The log spins, and a thin, flexible layer of wood comes off it, only 1/16 of an inch thick. It unfurls like a gift wrap ribbon, only instead of glitter, there's warmth, steam, and the smell of fresh wood. And instead of music, the roar of hydraulics and the rhythmic rustle of the plywood roll. This ribbon is veneer, the basis of plywood, its soul. It comes out without stopping, tens, sometimes hundreds of feet long, is rolled up or automatically cut into large sheets, typically 4 by 8 feet. Peeling is a sensitive process. The log must be straight, symmetrical, moist, but not too soft. If it cracks, it's over. The veneer will have holes or waves, and the plywood won't be grade A, but oh no. Operators carefully monitor every movement. On the display, graphs of speed, pressure, layer thickness. Cameras capture every knot. If something goes wrong somewhere, the machine stops in a second. And then they fix it, readjust it, and back to the fight. When the log is exhausted to the core, what remains is a core, a few inches thick. It's automatically ejected to the side, to be later processed into sawdust, fuel, or wood chips. Nothing is wasted here. Everything will be used. And the veneer sheets, hot, pliable, still smelling of steam, race onto the dryer. But for a moment, as they come off the knife, they are incredible. This is living wood, which has already lost its tree form, but has not yet become plywood. It flows like water from a tree. It dances like a gymnast's ribbon. It rustles like paper, but carries the strength of a trunk. As soon as the veneer ribbons come off the knife, they are still damp, steaming, like leaves after a thunderstorm. And so, they are picked up by an automaton, pulled into a drying line, incredibly long, like a train in Texas. Inside, hot air, about 200 degrees Fahrenheit. Flows are accelerated by fans. The sheets race along a conveyor belt at a set speed. 10 or 15 minutes, and the veneer comes out dry as a bone. And at the same time, still flexible, because if you over-dry it, it will break like a chip. And if you under-dry it, the resin won't stick later. Everything, down to the micron, down to the second. It's not just automation at work here, but also the intuition of the dryer operator, who can tell by sound and smell. This oak is still damp. Next, sorting. Veneer sheets, dozens, hundreds, roll onto an inspection platform, where operators or modern cameras with artificial intelligence decide where each should go. A sheet without knots, perfectly even, goes for the face layer, the highest grade. With small cracks, to the middle, with large defects, into the inner layers, or for backing. Everything that doesn't fit is shredded and sent for recycling. Nothing goes to waste. The selected sheets are fed to glue applicators, huge drums that evenly roll on a waterproof phenol formaldehyde resin. It's dark brown, thick, sticky, smells sharp, like a school desk after woodshop class. And here, everything is important. The layer of glue, the temperature of the sheet, the direction of the fibers. Because plywood isn't just glued sheets, it's cross-laminated layers, where each layer runs perpendicular to the previous one. This is how it gets its mechanical strength, flexibility, and resistance to warping, like a bulletproof vest, but made of wood. The finished sandwiches of several layers are placed in a giant hydraulic press that applies pressure from 150 to 250 psi, at a temperature of about 300 degrees Fahrenheit. Inside the press, it's hell, but a controlled one. 10 minutes and the resin hardens, binding the fibers into a single body. The plywood becomes monolithic, hard, sanded from the inside out. This moment is the culmination of the entire process. Here, from wood and glue, a plywood sheet is born, ready for battle. Coming out of the press, the sheet is still hot. It is laid on a cooling conveyor, a wind tunnel where cold air draws off the residual heat. Then, a sanding machine. On both sides, large rollers with sandpaper remove microns of irregularities, even out the surface, remove excess glue. Next, cutting into standard formats, usually 4 by 8 feet, although a customer can request 6 by 10 feet, or even mini sheets. Then, quality control, scanning, marking, packaging. Each sheet is marked with a code, a grade stamp, a production date. It is packed in stacks of 40 to 60 pieces, wrapped in stretch film, and off to the warehouses. Each sheet that leaves the factory has passed through water, steam, blades, fire, a press, and saws. And now it can be anything. It becomes a wall in a new house in Kansas, or the back of a chair in a New York coffee shop. Sometimes, the level of a stage in a music school in Iowa. Another time, the roof of a house in Mississippi, the floor of a trailer somewhere in the middle of Arizona, or even the body of a truck speeding down I-80 at night. And each time, thousands of layers of wood hold together, as if whispering, "We are plywood. We are stronger than we look." What made of plywood is right next to you right now? Every year, over 1 billion gallons of paint are produced worldwide, enough to cover the entire area of the US 10 times. But how is paint, capable of withstanding the heat of Dubai and decorating skyscrapers like the Dubai Creek Tower, born from crude oil? This isn't just a solution in pigments. It's a symphony of pipes, reactors, and ultrasonic checks, where precision is more important than a milligram. From the oil refining column to robotic arms that carefully package each can. And if you watch this video until the end, you'll learn one little known fact that paints the entire industry in new colors. Tankers of oil are drained into separation tanks. Here, at a height of about 60 feet, stands the fractional distillation column, a labyrinth of pipes and valves that transforms boiling liquid into a stepwise separation of hydrocarbons. Vapor rises through mesh trays with intervals of 10 inches, each of which filters out a separate fraction by its boiling point. At about 350 degrees Fahrenheit, kerosene is separated, then diesel, lubricating oils. And closer to the top, light aldehydes and aromatic hydrocarbons, which will later become the basis for the chemistry of polymer paints. After fractional distillation, each selected fraction is directed to the reactor hall through a network of high-precision pipelines that stretch for tens of yards along a technical corridor. The pipes are made of hardened steel, 4 inches in diameter, with an inner Teflon coating that prevents corrosion and chemical wear. The flow of fractions is regulated by electronic valves that react to real-time temperature and pressure readings. Each section of the pipes is equipped with sensors that read the liquid's viscosity, impurity level, and delay time at filtration nodes. Booster pumps with ceramic rotors pump the fractions at a speed of 15 gallons per minute, preventing turbulence, so that the molecular structure doesn't change. At turns, the pipes are enclosed in cooling jackets that maintain the temperature within 120 degrees Fahrenheit. Finally, before entering the reactor hall, the components undergo a final check, using a spectrometer installed directly in the injection unit. The flow pulses evenly, like blood in vessels. Precision and rhythm here mean the quality of the paint that will take on the desert sun. In the industrial zone, the temperature reaches 600 degrees Fahrenheit, and the air is saturated with the smell of toluene and benzene. Here, the first stage of synthesis begins, cracking and alkylation. Huge reactors, resembling vertical steel barrels 20 feet high, mix the components under a pressure of 60 psi. In 8 hours, these compounds change their structure, acquiring the properties of polyurethane, the basis of a durable paint for exterior coatings. Filtration occurs through tubular separators with titanium membranes less than an inch thick. They are capable of passing only molecules of a certain size, filtering out residues of unwanted reagents. The hot mixture, which has just passed through reactors, filters, and pigment mixers, enters the packaging sector. Here, under the control of sensors and robotic manipulators, the paint is poured into 5-gallon steel containers, a standard that allows for easy transport and storage of the material on skyscraper construction sites. The containers are not just cans. They are made of chrome-plated steel, with an internal anti-corrosion coating that withstands the aggressive chemical components of the paint. Before filling, each can undergo a preliminary leak test. Laser sensors scan its surface, and robotic grippers rotate the container at various angles to detect deformations. After this, the paint is poured through injection heads that control the volume with an accuracy of 1/100th of a gallon. The mixture temperature is about 100 degrees Fahrenheit, which ensures optimal viscosity for pouring. Filled cans are transported by conveyor to the polymer sealing shop. Here, one of the most important stages takes place: ultrasonic inspection. The cans enter chambers where high-frequency waves pass through the metal shell. Sensors detect any structural violations, microcracks, air pockets, weak welds. If a defect is found, the can is automatically rejected from the line and sent for reprocessing or disposal. Those that pass the inspection move on to the marking station. Here, laser printers apply a heat resistance index, production date, mixture code, and also a QR code to the can's surface, which allows for tracing the entire production history, from the oil field to the specific reactor. In some cases, an RFID chip is embedded in the lid, providing digital identification at the construction site. When the cans of paint have passed all stages of inspection, marking, and sealing, they enter the logistics zone, a place where engineering precision turns into a choreography of transportation. Here, in the loading shop, 5-gallon steel containers are placed on pallets, 48 pieces on each, taking into account weight, center of gravity, and stability. The pallets are wrapped in shrink film, which protects the cans from dust, moisture, and mechanical damage. Then they are marked with RFID tags, which allow for tracking each unit in real time. Automated forklifts, Electric machines with laser navigation pick up the pallets and transport them to the loading platforms. Here stand trucks with thermally insulated bodies, equipped with temperature and humidity control systems. In Dubai, this is critical. The paint must not overheat or cool below 60 degrees Fahrenheit. Otherwise, its structure will change. Before loading, each truck is scanned. The cleanliness of the body, the tightness of the doors, and the functionality of the cooling system are checked. Loading takes place via hydraulic platforms that level the height of the truck body with the warehouse level. Robotic arms, equipped with pressure sensors, carefully place the pallets inside, following a placement scheme. Heavy, closer to the axle, lighter, to the doors. After loading, the system automatically records the position of each pallet, updating the route in the logistics database. The trucks set off for the construction sites of skyscrapers, for example, to the Dubai Creek Tower or Wanza Abail. On the way, each truck is accompanied by GPS monitoring, and the driver has a tablet with temperature updates inside the body. If the indicators go beyond the limits, the system sends a signal to the central server, and the cargo is redirected to a backup warehouse. On site, the paint is unloaded using mobile cranes or elevators if the construction is already at a height. The cans are lifted to the floors where painters in heat-resistant suits are working. And when the first stroke is applied to a concrete panel, the final act begins. The paint, which has traveled from oil to pigment, becomes part of Dubai's architectural canvas. In the US, the paint market is valued at over $34 billion, with over 1,003 million gallons of paint produced annually. In the UAE, about $100 million and significantly smaller volumes, but with a high share of exports. In the US, over 300,000 workers are employed in the paint industry, while in the UAE, the market is more automated and less labor-intensive. Both countries are moving towards environmental standards. In the US, paints with low VOC content are popular, and in the UAE, nanocoatings with thermoregulation. The Jotun Company has plants in Abu Dhabi and Dubai, and National Paints owns one of the largest paint production complexes in the Middle East. In 2025, the Jotun Company continued to show stable growth. In the first 4 months of the year, its operating revenue was over $1 billion. This is 4% more than in the same period of 2024. The company employs over 10,600 people, has 67 subsidiaries, and 40 production facilities worldwide. Exports to the US account for less than 1% of total sales, which reduces risks associated with tariff changes. What information impressed you today? Every year, over 2 billion tons of trash are generated worldwide. It's as if every inhabitant of the planet threw away 5 kilograms of waste every day. But did you know that this trash is now not just a problem, but a goldmine for a new industry? In workshops where just yesterday dirt and danger reigned, today high-tech hunters are at work. Robots that see more than the human eye and can sort in seconds what humans struggled with for years. And this is just the beginning. If you watch until the end, you'll find out how one teenager's idea changed the fate of the entire ocean. The waste management sector is undergoing a technological revolution thanks to the implementation of artificial intelligence and robotics. At modern recycling plants, robotic manipulators, controlled by complex algorithms, sort waste with incredible speed and accuracy. Computer vision systems identify different types of materials, such as plastic, glass, paper, and metals, which significantly increases the recycling rate and reduces the amount of trash that ends up in landfills. On a wide conveyor belt, a continuous, chaotic stream of what we've thrown away: plastic bottles, crumpled cardboard boxes, aluminum cans, milk cartons, glass bottles. To the human eye, it's just trash, almost impossible to sort through. And for a human worker, it's hard, dirty, and dangerous work. And so, above this stream, like a relentless hunter, it hovers, the sorting robot. This isn't a humanoid android from science fiction movies, but rather a high-tech industrial manipulator, similar to a giant steel arm mounted above the conveyor. But all its magic is inside. Its eyes are not just cameras. They are complex multispectral sensors that see the world differently than we do. They can distinguish materials by how they reflect light, analyze their chemical structure, and shape in a fraction of a second. The heart and brain of the system is artificial intelligence. Before getting on the job, this AI underwent intensive training. It was shown millions of images of different types of waste, just like you would show a child a million photos of apples until they learned to recognize them flawlessly. In the same way, the robot learned to identify PET plastic, used for beverage bottles, HDPE, a denser plastic for canisters and bottles, paper, cardboard, various types of metals, and glass. And so the action begins. The conveyor is moving. The camera continuously scans the stream. The AI analyzes the images in real time. Target identified. Aluminum can. It sends a signal, and the steel manipulator makes a lightning-fast, almost imperceptible to the eye, move. A pneumatic suction cup, or a mechanical gripper, gently but firmly grabs the can, lifts it above the stream, and with a precise movement, drops it into the corresponding container on the side. Before the can has even landed, the robot's eye has already spotted a water bottle, and the arm flies to a new target. Speed? A human can't compare. Some models can perform 100 manipulations per minute. That's more than 1 grab per second. Accuracy. The robot doesn't get tired, doesn't get distracted, and doesn't make mistakes due to inattention. Its sorting efficiency reaches over 95%, which significantly improves the quality of secondary raw materials. It can work around the clock, stopping only for maintenance. This isn't just a replacement for manual labor. It's a quantum leap that makes recycling much more efficient and economically viable, turning the problem of trash into a real resource for a new industry. The sorted materials, piles of hard plastic, bulky metal structures, wooden pallets, lie in separate mountains. They have been sorted, but are still too large, too awkward to be given a new life. This is where the true heavyweight of the recycling industry comes onto the scene, a machine whose job is controlled, brutal force. This is a rotary shredder. Externally, it looks like a huge steel box, but its heart is a massive heavy rotor, studded with rows of extremely strong, hardened steel teeth or hammers. This is not just a machine. It's an insatiable beast, powered by a powerful motor that provides colossal torque. Its task is simple, but critically important: to shred. When material is fed into its huge maw by a conveyor or a manipulator, be it an old car bumper or a whole pile of plastic barrels, a spectacle of unstoppable power begins. As it rotates, the rotor's teeth grab the objects, pull them inside, and with a deafening roar and grinding, tear them into pieces. There's no room for delicacy here. Hard plastic cracks, metal bends and tears, wood turns into splinters. This process is a demonstration of pure physical force, aimed at one goal: size reduction. But why this destruction? It's not senseless annihilation, but a key preparatory stage. First, the shredded materials become uniform in size, making them much more convenient for transportation and further processing. Second, it's a process of liberation. The shredder breaks down complex objects into simpler components, making it easier to separate different materials from each other in subsequent stages. And most importantly, it creates the ideal raw material for further recycling. A pile of small plastic pieces is much easier to melt in a granulator than whole bumpers. Huge accumulations of plastic in the world's oceans, such as the Great Pacific Garbage Patch, are one of the most acute environmental problems of our time. By the way, do you believe that this patch doesn't exist? However, thanks to bold engineering solutions, there is hope for cleaning up the marine spaces. The problem is so gigantic that it seems unsolvable. how can you clean up something the size of several countries? Most people just threw up their hands, but not Dutch teenager Boyan Slat. In his mind, a bold yet brilliantly simple idea was born, which grew into one of the most ambitious environmental projects of our time: the ocean cleanup. The principle of the project is not to chase plastic all over the ocean, but to make the ocean itself deliver the garbage to a trap. For this, giant U-shaped barriers were created. This is not just a net, but a complex engineering structure consisting of a long, floating boom on the surface that prevents plastic from floating over it, and a deep mesh skirt underwater that traps the garbage, but allows marine life to swim freely underneath. The most interesting thing is how this system moves. It has no engines. It passively drifts, carried by the same forces that move the plastic: wind, waves, and ocean currents. But thanks to its design and a large sail above the water, the system moves slightly faster than the plastic passively drifting in the water. This creates a small but constant difference in speed. The barrier, like a giant shepherd, slowly but relentlessly gathers its plastic flock inside its U-shaped arch. The path to success was not easy. The first prototypes broke under the pressure of ocean storms, and unforeseen engineering problems arose. But after a series of trials, errors, and significant improvements, the system began to work effectively. Now, from time to time, special support vessels approach the filled barrier and, like giant garbage trucks, unload the collected tons of plastic. This plastic, from old fishing nets to tiny fragments, is brought to shore, where it is sorted and sent for recycling, closing the loop. Thus, an idea born in the mind of a young dreamer has turned into a real, working technology that offers hope for cleaning our oceans. Realizing that cleaning up the ocean without stopping the flow of trash entering it is like bailing water out of a leaking boat, the ocean cleanup team asked themselves a logical question: couldn't we just plug this leak? After all, research shows that the vast majority of plastic enters the world's oceans through just a small number of the most polluted rivers in the world. Thus, the Interceptor was born, a technology aimed at tackling the problem at its source. It looks like an elegant, futuristic catamaran, anchored in the middle of a river. It is completely autonomous and runs on 100% solar power, thanks to the panels covering its upper part. Its design is thought out to the smallest detail to be as effective as possible, and not to interfere with navigation.